Dynamic behavior of materials. The study of materials' behavior in extreme environments and the development of new materials for such environments has become a vital research area for materials scientists and engineers in the 21st century. Mechanical properties of materials under dynamic loading are considered an important area of research and development in the defense, automotive, and aerospace industries. Under dynamic loading conditions, the inertial effects come to play an important role in the deformation behavior of the material. Many materials exhibit strain rate sensitivity at higher strain rates, i.e., flow stress dependence on strain rates. Also, the failure mechanisms under high strain rate loading conditions are generally different than those that occur in a low strain rate. Furthermore, the deformation and failure mechanisms are controlled by the microstructure of the materials. This course will be important to mechanical, materials, and civil engineers to understand materials behavior for ballistic applications, explosive forming or welding applications, automotive and aerospace applications. Dynamic behavior of materials. Intended audience: mechanical engineers, civil engineers, materials engineers. What will I learn? Week 1. Introduction. Dynamic deformation and failure. Week 2. Introduction to waves, elastic waves, types of elastic waves, reflection, refraction, and interaction of waves. Week 3. Plastic waves and shock waves, plastic waves of uniaxial stress, uniaxial strain, and combined stress, Taylor's experiments, shock waves. Week 4. Shock wave-induced phase transformation, explosive material interaction and detonation. Week 5. Experimental techniques for dynamic deformation. Intermediate strain rate tests, split Hopkinson pressure bar, expanding ring test, gun systems. Week 6. Review of mechanical behavior of materials, especially metals, elastic and plastic deformation of metals, dislocation mechanics. Week 7. Plastic deformation of metals at high strain rates, empirical constitutive equations, the relationship between dislocation velocity and applied stress, physically based constitutive equations. Week 8. Plastic deformation in shock waves, strengthening due to shock wave propagation, dislocation generation, point defect generation and deformation twinning. Week 9. Strain localization, shear bands, constitutive models, metallurgical aspects. Week 10. Dynamic fracture, fundamentals of fracture mechanics, limiting crack speed, crack branching and dynamic fracture toughness, spalling and fragmentation. Week 11. Dynamic deformation of materials other than metals, polymers, ceramics, composites. Week 12. Applications, armor applications, explosive welding and forming,